Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is You Ask, We Answer, a panel discussion on battery testing. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the technical moderator for today's presentation and supporting you on any technical issues or questions for our panel. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during our discussion here today or integrate them to the best of my abilities. Additionally, a certificate of attendance, a copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our host today is Len Holitz, Megger's Director of USA Sales. And I'm going to hand the floor over to him. After you, Len.
Hi, good day, everybody. This is a unique event as it is a panel of You Ask, We Answer. So as many of you may be, I'm working from home in order to maintain isolation with social distancing. And if you don't know me, I joined Megger in 1986 as an applications engineer for Multi-Amp Institute, which led to a career in supporting the electric utility market through product sales and services. My current role is Director of USA Sales, and let us begin today with the next slide. So associated with the You Ask, We Answer, many of the webinars that we produced up to this point have been best practice series, which are designed to share information and topics such as with batteries, ohmatic testing, NERC standards relating to battery testing, load testing, and in the past and future webinars can all be accessed through our Megger.com website, just like webinar at the top banner. This panel is live so that you can ask questions during the program. As you registered for the event, you are asked to provide questions to start today's conversation with our industry experts. We will also be responsive to new questions, so I encourage you to type in those questions in the chat, and let's meet our panelists today. So up first is Andy Sagel. Andy is the product manager out of Valley Forge, Pennsylvania. He first joined Megger through an acquisition of Metrosonics power quality instruments some 20 years ago. He is our in-house specialist for ohmatic battery testing and power quality applications. He's a member of the Battery Standards Group with IEEE. And Andy is a welcome participation today to answer your questions related to the factory and our product. Next is Curtis Ashton. Curtis works for American Power Systems, which is a subsidiary of East Penn, a manufacturer of storage batteries. American Power Systems specifically offers battery testing programs for clients. He brings to the conversation several decades of working with batteries and is considered a subject matter expert in his role as Director of Training. Notable is Curtis is the current chair of the Energy Storage and Station Battery Group of IEEE Power Engineering Society. Also has been a member and current member of American National Standards Institute Alliance of Telecommunication and Industrial Solutions, and the IEEE Power Electronics Society. Get tongue-tied with all that. Next. And welcome, Curtis.
Thanks.
Next is, John Kim. Intersys batteries are well known in our industry for energy storage solutions. And John Kim is their Director of Utility and Industrial Systems. Megger has worked with John a number of years to provide joint best practice seminars and is a welcome addition to our panel today. He's had over 30 years of battery construction, design, maintenance, troubleshooting, and can offer an insight from battery manufacturers to your questions today. Next is Sanket. Sanket Bolar joined the Megger Technical Support Group in Dallas, Texas, in 2015. He has a master's degree of electrical engineering in power systems from North Carolina State University, and he has presented a number of our webinars and training sessions, again, that you can find at megger.com. Thank you, Sanket, for being here.
Thank
you. Volney Naranjo is our senior applications engineer associated with our technical support group. And I met Volney when he was a client purchasing Megger products. So he was a user of these tools in the field before he ever came to work for us in 2011. As an electrical engineer, he participates in the IEEE Energy Storage and Station Battery Group and is often published as a subject matter expert at numerous trade shows. Thank you for joining us, Volney.
Thank you.
Associated with today's topics of the You Ask, We Answer battery session, we're going to follow these questions underneath the categories of maintenance, load testing, ohmatic testing, some miscellaneous questions, and if we have time, we will cover the NERC standard compliance, and we can cover other energy storage technologies at the end. A special thanks to our panelists who joined us today, and for you who are viewing us and submitting the questions. So let us begin with our panel and the first questions that you selected as you're registering. So under general maintenance questions to the group, the first question is, how do you know when a battery is not charging effectively? And this came from Keith Cuffey. Andy?
Yeah, basically when a battery is not charging effectively, one of the first things you're going to look at is you're going to look at that float voltage on that battery, okay? Now, one of the problems I've seen in the field that occurs when people take a measurement on float voltage is that they will tend to use a digital multimeter. So that's one thing to be careful of because of the high impedance on it. That high impedance input could actually cause a false reading if you have a high, if you have a battery with low capacity, you will not necessarily see it. So typically you want to use something that has a lower impedance on it to take those type of measurements. But again, when you have that low, if you have a battery that's not adequately charging, again, you want to check that float voltage. And the other big thing is to check the strap resistances. If your strap resistances are off, if you have high strap resistances, what will happen is you'll get larger voltage drops across the string, and this can lead to lower float voltages on the batteries, not allowing them to fully charge up. And of course, the other thing that you could also have is you could also have a short in the battery, where you'll see a lower voltage, and you'll also typically see a lower impedance along that accompanies that as well.
Curtis, you want to respond?
Yeah, I wanted to add about float current, which is a little harder to measure, but that will tell you truly when your battery is fully charged or if it's not fully charged yet or if it's getting too much charge current. And so a clamp-on ammeter, from a portable instrument perspective, a typical clamp-on ammeter is not capable of reading the low battery float currents, which are in the order, depending on the battery size, of a few milliamps up to several hundred milliamps. Most of your typical AC/DC clamp-on ammeters measure no lower than 100 milliamps. And so you're not going to get an accurate reading on especially smaller batteries. So you have to buy a clamp-on ammeter that's capable of reading in the tens of milliamps or the single milliamps for DC, not AC. And you have to zero the meter right next to the cable right before you clamp it, before every single measurement. And so if you need recommendations on who makes those type of clamp-on ammeters, because there's not a lot of them out there, I've found about 8 that will work. Feel free, my email will be shared at the end of the presentation. Feel free to email me and I'll tell you the different clamp-on ammeters that I've found that are out there in the market that would measure battery float current. And so what happens is when the battery gets fully charged, the float current will drop off in the milliamp range. And if I take 3 successive readings over 3 successive hours, I know that it's fully charged when those stay within about 10 to 20% of each other. At that point, I know that I'm fully charged.
John?
I just want to add that if you want to know what the float current or proper float current should be when they're fully charged, you can contact the manufacturer and we'll be happy to provide that answer for you. As a rule of thumb, we would say something like flooded batteries, VLA, vented lead acid, you would be about 20 to 30 milliamps per 100 amp hours, and VRLAs are a little higher, but best way to get that information is to go to your manufacturer and ask for that information.
So that actually took care of the question from Justin Musgrave, which was the best way to implement flow current testing into a maintenance program. So I noticed that a lot of these questions are being asked from numerous individuals, so they're all in the same frame of mind. I think the next question leads into this is are float voltage settings the same for valve regulated acid and vented lead acid batteries?
Can you repeat the question, Len?
So it's are float voltage settings the same for VLA and VRLA batteries? Okay, Curtis?
Excellent question. Generally, no. There are exceptions. So you have to look at the manufacturer's recommended float voltage. So for example, a traditional utility battery for 125 or 250 volt DC plant is a 1215 specific gravity battery. So the electrolyte mix, the ratio of acid to water determines the float voltage. And also VRLAs actually tend to float a little bit lower than a similar flooded battery would do for the same specific gravity because you can't replace the water. So you want to make sure you don't get rid of the water too quickly. So the other thing that I would say is, for example, if you want to float a parallel string of VRLA with a flooded string, you need to look at the float voltages. And for example, there are some low gravity VRLA cells that are available from a couple of different manufacturers at least that can float in parallel with 1215 specific gravity batteries. But generally, no, the specific gravities are too different.
John, you had something to add?
Yes, as Curtis mentioned, the specific gravity definitely has plays a big factor in determining the float voltage, but also the type of alloy that you use, lead calcium versus lead antimony, that makes a difference as well. Even for VRLA, although majority of VRLA batteries are lead calcium VRLA, you have other products, pure lead. EnerSys has a thin plate pure lead TPPL product, which floats at a slightly different voltage than lead calcium. So again, the best way is to go to the manufacturer's brochure or spec sheet and see what that setting is, and that will make then you use that information to set the proper float voltage, because they can be all different.
Andy?
Yeah, I just want to add just one thing real quick is also when you look at the installation guide on some of these, the float voltages may also be temperature compensated. So you may have to adjust it based upon that temperature.
Okay, that's a good point, Andy. Thank you. I did have a follow-up question from Joseph Dingle, and I apologize if I pronounce any of these names wrong. And it's to Andy talking about the voltmeter. It states high impedance voltmeter readings can be somewhat misleading in some power applications due to phantom effects. Is there a recommended loading for a cell based on amp hour rating to ensure the reading is valid?
I have never seen anywhere where I have a actual recommended value. We use about 10K on ours, on our meters, and we have always seen that, again, we've always seen good readings on them. And again, where you're going to really run into a problem here is when you get into scenarios where you have batteries that have very low capacity in them. This is where you're going to see the difference in the reading when you're using a high impedance meter. So usually when I see that difference, these batteries are usually pretty shot, to be basically honest with you.
And Curtis?
Yeah, I was going to ask Andy, and hi, Joseph, long time no talk. I was going to ask Andy, when you talk about a low resistance or low impedance meter, I'm guessing that you're talking about an ohmic test set.
I'm talking about any digital multimeter. I'm talking
Right.
about its input impedance. So that if you have a battery with a very low capacity and you're just putting 2 or 10 meg across it, you're not going to see any, it'll still give you a good reading. If you put something that has a low input impedance, like around the 10K mark, it puts a very small load, but the battery has very little capacity, you're going to see that lower voltage on it.
Right, but the ohmic meters that are available that measure both internal ohmic and voltage, they have low internal impedance, correct?
Yes, that is correct.
And only follow-up?
Yeah, well, a little comment in visiting customers and showing or in performing training on our instruments. I was once shown at a utility that when they take measurements with a regular voltmeter, what they do is that they put a resistance in parallel there to the input of the voltmeter. So it's kind of a quick way to get that purpose, to achieve that purpose of getting that low resistance in the terminals of the voltmeter, or low impedance there. So that's one other way you can do it, like in a quick way.
The only thing that I would add there, Andy's talking specifically about batteries with extremely low capacity. 99% of the time when you're talking about a battery that's got a lot of charge in it, a standard digital multimeter is going to work just fine.
But I've seen where that has come back to bite them, so it's just something to always be conscious of.
The next question is from Garvin Russ, and it states, what is a better health indicator of battery health, impedance or load testing? What can one show you that the other can't? And let's hear from Sanket first on this one.
So when you talk about ohmic testing or impedance testing, and you talk about load testing, these are two different tests which look at two different things. The load test is, I would say, the true test of the battery, because you're actually finding out how the battery would function. And the function of the battery is to provide current to a load. So you actually test the capacity of the battery when you do a load test. You actually pull current from it and you monitor the battery voltage, see how it discharges. So it truly tests the battery. At the same time, there is some effort involved. It consumes more time, needs a load bank, needs a backup load bank, things like that. So what you can do is an ohmic test can be done as part of your maintenance program in the time interval between load tests, where you kind of monitor the electrical path that is the battery string. And that's what ohmic testing is. You're not drawing current from the battery. You're not testing how the battery discharges, but what you are checking is the condition of the electrical path. You're checking at the impedance of the cells. You're checking the inter-cell connections. So these are two different things, and a good maintenance program would kind of implement both tests, so that when you're not actually doing load tests are done typically once every 2, or depending on the type of battery and depending on the program that you have, they're done once in every n number of years. So in between the time, you can in between load tests, you can monitor the condition of the battery through ohmic testing. So both of these tests are two different tests which look at two different aspects, but both of them can be used effectively in a good battery battery testing program.
Tom Schumacher actually had a question that led into what we're just discussing. And his question is, what is the maintenance frequency to lead acid batteries for substations located within manufacturing plants. And this could be asked in two different ways: manufacturing plants versus utility application, where it might be in a substation, but also on the actual maintenance frequency associated with batteries as it relates maybe to ohmatic test or load testing. So who would like to take this one on? Curtis.
So let's talk a little bit about maintenance frequencies as what's actually required by law and what's wise to do and what's recommended to do. So the only law that I'm aware of is NERC, and that's not going to apply to a substation in an industrial facility typically. That's only going to apply to the substations that the electric utility owns typically, and their generating stations. So NERC has specific frequencies that you have to do specific maintenance items for. That's PRC 005, and those vary quite a bit, and it's a long answer to go into exactly what those are. However, everything beyond that, like when you look at everything else, it's all a recommended practice. I don't care if you look at NFPA 70B, I don't care if you look at NETA MTS or the IEEE recommended practices for battery maintenance, the frequencies are recommendations. The only caveat I'll give to that is if your warranty statement with your battery manufacturer says maintain it this often or else I won't honor the warranty, then you probably ought to maintain it that often. And so there's some basic things that you need to take fairly frequently, like your float voltage and your temperature. Those need to be taken often enough to where the battery manufacturer will honor your warranty. As far as the 125 volt DC systems in an industrial plant, I'm assuming you're talking about vented lead acid batteries. IEEE 450 is the recommended practice from IEEE, but it's, in my opinion, it's probably overkill in terms of the frequencies for a substation in an industrial plant, because it's really built around a nuclear generating station that you really care about. So the frequencies are probably a little bit overkill. I would generally recommend quarterly, triannually, or semi-annual routines for those types of sites.
Okay, John.
Well, I'll be the first one here to say it depends. Depends on the customer and what their standard is or what their procedure is. Generally, they would model their procedure after IEEE 450 for flooded VLA and 1188 for VRLA, and the manufacturers participate in these documents. So if you're following IEEE documents, manufacturers will accept those maintenance number that Curtis mentioned as part of warranty requirement.
We had a general question that came in from the group, and it's like, how do you thermal runaway from propagation? And I imagine with thermal runaway associated with sealed batteries. John?
Well, thermal runaway happens to all batteries. And if we're talking about lead acid, yes, you're correct, Len, that for VRLA it happens a little more frequently, but it does happen to flooded as well. And I would say the first thing you need to do is shut the power off. Make sure there is a way of detecting it, whether it's through thermal runaway detector, which can measure temperature, can measure float current and all that, and shut the power source off. And I would say open the room and put a fan on it or some way to cool it down and lower the temperature that way. And thermal runaway doesn't happen. Thermal runaway is when batteries, when they're on charge, it will create a little bit of heat, but it's not detectable. But once the battery starts to go into situations where they're drying out or generating more and more heat, they're getting overcharged, or if the environmental temperature itself is high and it cannot dissipate that heat, then it will get so hot that it will actually melt down. And in some cases, it just makes a ghastly mess. So you want to avoid that as much as possible. And one way to do that is to detect it early and shut the power off and and cool it down as well as ventilate the area.
Okay. Curtis, and Andy. So let's go to Curtis first and then to Andy.
So a couple of things. John mentioned that high temperatures help with thermal runaway. They can exacerbate it, but they don't cause it. I want to be clear on that there are thousands and tens of thousands and millions of batteries deployed in very hot desert environments that are lead acid, and they're not in thermal runaway. They have a greatly shortened life. So the way to easily detect it is to measure the difference between ambient and the battery post temperature on a VRLA. So if you're measuring the difference between ambient and the battery post temperature, if you're reading more than about 5 degrees C of difference, you're probably in the beginning stages of thermal walkaway. And if you're reading more than 10 degrees C difference or 18 degrees Fahrenheit, you're probably in thermal runaway. Now, the person asked about propagation. Propagation in lead acid batteries is not common of thermal runaway. That term comes mostly from the lithium ion industry, where a thermal runaway of one cell creates a jet of heat that jets out of the end of the cell and catches the next cell on fire. That doesn't happen in the lead acid battery. However, in a lead acid battery string, you can propagate from the cell that's in thermal runaway somewhat to the nearby cells because all that heat is being generated and is in the environment around the other cells in the string. You're unlikely to spread it to another string though, even if it's nearby, because the current's not the same in the two strings, and so you're not getting the same I²R heating. So most of the time propagation is a lithium ion thing, not a lead acid thing.
Right. Andy, you still?
Yeah, the only thing I was going to add into that is also you're going to see the float current begin to rise as you start getting into, Curtis, thank you for saying thermal walkaway, because I really think that's the better name for it, because it's not going to happen overnight. But a temperature compensated charger when you're using VRLA batteries is recommended to help deter that. And Curtis, you're absolutely right. Propagation is typically with the lithium ion batteries. And one of the things that's crucial in there is the rack system you put in to help eliminate propagation when you do have that thermal runaway.
So I'm going to change to the next topic area, which is battery load or discharge testing associated with station batteries. And as we go through the next several questions, it is related directly to load testing. What the first question is why is it important to measure both the float voltage and open voltage before doing a capacity test? Sanket, did you want to take this one first?
Sure. So it's a good practice to measure the float voltage and the open voltage before doing a capacity test. Float voltage is the voltage which the battery is on when it's connected to a charger and it's on float. And float voltage basically just the right amount of voltage which it needs to be maintained on for it to function properly. Now, before you start the load test, you disconnect the charger, but before you start drawing current from the battery, you have to measure the open circuit voltage, and you will see that there is a little bit of a drop from the point when it's on float condition to the point when it's on open circuit, and that drop kind of tells us about the health of the battery. It tells us about the state of charge of the battery. If the battery state of charge is low, then you will see more of a drop and you will see a lower open circuit voltage. If the specific gravity is what it's related to, and if the specific gravity is low, which would be the case if the battery is not charged enough, then you would see a greater drop in the voltage and you would see a lower open circuit voltage.
And Curtis.
So the IEEE recommended practices on discharge testing recommend, just like the questioner asked, a float voltage, an open circuit voltage, an end of discharge voltage on each individual cell, and sometime in the middle. It doesn't really matter probably halfway through the discharge test is probably a good idea. And the ones that tell you the most are the ones during the discharge test. So we've talked about the float voltage and the open circuit voltage, and they can tell you when you've got some really bad cells. But the ones that tell you the most are the two that you take during the discharge test and at the end of the discharge test on each individual cell. The float voltages will vary quite widely sometimes in a series string. For example, on a series string of 1215 specific gravity cells in a utility that's got 60 cells, I might see voltages all the way from 2.14 up to 2.35 on float, and it doesn't mean anything. Those are all good. They're all fine. I can't really tell much from that. However, like Sanket said, if I go to take open circuit measurements, and all of a sudden one of them is clear down at 2.0 volts right after I took it off a charge, that's way too low. I should be seeing something in the 2.07 to 2.10 range, probably. And then if I go on discharge, what will happen is all those disparate voltages that we saw from 2.14 to 2.27, they'll start to come together during the discharge. And typically they'll be within anywhere from 300ths to 800ths of each other. If you see more than that, in other words, if I'm halfway through discharge and I take a bunch of readings and all the cells are 1.95, 1.96, 1.97, 1.95, and all of a sudden I see one that's at 1.78, that's a weak cell. That tells me far more than the float voltages will ever tell me, because now it's loaded, and now you see how it really performs under load.
Right. Thanks, Curtis. Volney, you wanted to add something?
Yeah, a comment, and Curtis, correct me if I might be wrong on these. The advantage of doing that open circuit voltage measurement is that if you see that the cell is weak, you might take the decision of removing that cell from the string before starting the test, because it's a long test, it's an expensive test, and you don't have too much time to bypass the cell or to remove the cell during the test. So you might want to remove it before the test. Is that kind of a recommended practice?
It's not a recommended practice, but I like the idea. What the recommended practice in IEEE is if you see cells that reach the minimum voltage early, you have to bypass them during the test. And like you said, you're only allowed 7 or 8 minutes, I forget the exact number, to do that bypass. And so I remember one of the questions that was submitted by the attendees here was, what should I do to be ready before a discharge test? One of the key things is to have bypass cables ready at the ready. But I like your idea. If you see a really weak cell on the open circuit test, you can take it out right from the beginning. And then maybe you run a separate discharge test on that individual cell later to find out what its capacity is. But that's a really good idea, because you don't have a whole lot of time to do the bypasses. So I like your idea.
Okay.
John?
Just a quick comment. So bypassing a cell is feasible on longer duration discharges, but if you're doing UPS discharges where you're doing 10 minutes or 15, forget about it. It's almost impossible.
Okay. That actually kind of leads into some of these other questions here. I think we'll take Steve Dilithium. He wrote, to perform or not to perform an equalize or high rate discharge before performing a battery test or a load test. So do you do an equalized charge before you do a load test?
Well, that's one of the questions that it's always answered with, it depends. So first of all is what battery you have. If it's a VRLA battery, you definitely want to consult the manual, consult the manufacturer, and probably not recommended to do, because you end up starving the electrolyte of the battery by too many equalizations. So, but it is important to run equalized charge, because you want to have your battery under a very good condition of charge. You want to know that any sulfation has removed. If you added water, you want that water to be mixed and converted into electrolyte, and you want to have the full condition of the battery for the test. It is a performance test. I always relate the capacity test like running a marathon. You prepare for the marathon. So that is what you're doing with the equalize. And also it's very important that after you equalize, that you let that battery go into an equilibrium, sit down there for 72 hours is the recommended practice in the IEEE standard, and let it sit down for 72 hours so thermal and electrical equilibrium is reached, and then you can run your test. So it's always important to determine if you need to do it for VRLA batteries, and for VLA batteries, I think you need to do it always.
Curtis?
I'll be the contrarian. I would agree on VLA. I totally agree with everything he said about VRLA to try to avoid that as much as possible. Boost charging, equalized charging. On VLA batteries, it's important on a new battery for a couple of reasons that you do the boost equalized charge. One has to do with the fact that some manufacturers do not fully form the batteries in the factory, and so you end up giving it enough charge to where it can pass the capacity test, the minimum capacity test. And also it may have been in storage for several months, and so you're, as Volney said, you're trying to get rid of that sulfation. Even though IEEE documents, and I'm the chair of the IEEE committee, even though they say to boost charge it every single time before you run this performance test, as a user, I want to know what my real capacity is when I'm down the road, not on a new battery. Go ahead and do the equalized charge on a new flooded battery or VLA battery. But when I'm down the road, Mother Nature doesn't tell me when it's going to cause an outage and tell me when the power is going to go out, so that I know how much capacity. I want to know how much capacity I'm going to have when Mother Nature takes the power out. So that's just me, just a contrarian opinion that you can find out your real capacity in when Mother Nature takes the power away from you just by simply running the discharge test.
John, you wanted to add?
Yes, I would say the best document that you can read is IEEE 450 as well as 1188, which gives you several options of doing capacity testing. And one of the things that Volney mentioned is 72 equalized 72 hours. That's covered under one type of test. What Curtis mentioned is in as found conditions, and that's covered under another little section. So I would say, for time's sake, I'm not going to go into in detail, but check with IEEE 450 and 1188, and it explains that very well.
Now, Volney and Curtis, you both mentioned, driving this load test beyond 100% capacity in your responses. So Arjun had actually asked, if a battery passes a load test at 100%, why do we continue to push the test beyond 100%, stressing the battery test even further? So why do we do that? John, you want to respond first?
Yes, as a manufacturer, when you do a initial, let's say you're doing an acceptance testing, and we want to set the baseline as best as possible, which means going beyond that 100% and going down to the preset cutoff voltage, whether it's 1.75 volts per cell or 1.81 or whichever. And establishing that baseline. Now, from that point on, any subsequent capacity testing you're doing, you can measure against something, rather than, okay, when let's say you're doing a 3-hour test, it went 3 hours, I'm going to stop, and all the voltages are up above 1.8. It really doesn't give you a lot of information. So I would say my recommendation as a manufacturer would be, just don't go below the low voltage cutoff, but go to that level, and now you have a good baseline.
All right, and Todd Johnson had a follow-up question, and maybe you could answer this one, Curtis. It is, can you estimate the loss of a battery life from 5 load tests over the battery in service years?
The simple answer to that is yes. So you can trending is super important in battery readings. And so like John says, if I get a baseline and then the initial capacity test, it's 95%, believe it or not, on most VLA batteries, the capacity will actually rise over the first several years. And so maybe 5 years in, when you do your next capacity test, discharge test, you might see 103%. And then it might start falling after that towards the 80% near the curve point. The point that I was going to add to what John said has to do with The fact that the batteries, in the first question, it seemed inherent to me that the person is worried about stressing the battery. I want to stress that the battery is designed to discharge to that end voltage John talked about, whether it be 1.75 or 1.67. It's designed to do that for typically hundreds of cycles. It can do most of them can do more than 100% depth of discharge cycles. So if I do 5 load tests in a battery life, I am not really robbing life from the battery. Key though, if you have an individual cell, and let's say my end voltage is 1.75 and I have an individual cell that drops below 1.6, for example, I need to bypass that cell before I continue the test or stop my test, one of the two. And the reason for that is I don't want to push the cell into reversal. And I run that risk once I get down around 1.5 volts, I run the risk of, if I continue to load it, to run it into reversal, which will permanently damage that cell.
Just quickly, what Curtis mentioned is very important. Once it reaches that low voltage cutoff, and if you continue to discharge that battery, that voltage will drop very quickly after that point. So from 1.5 down to half or even 0 is going to be a matter of minutes. So you need to be very careful. That's why I recommended cutting it off at recommended cutoff voltage, typically 1.75 or 1.67 for UPS. If you discharge to that point, you're fine. Batteries can handle that type of stress, if you want to call it that.
Right. And I know that the Megger product, doing a discharge test, not only monitors the overall system voltage, but also each individual battery cell with the battery voltage monitors as we're running the test, in order to profile that as we're doing the discharge. The next question was kind of an interesting one, and this comes from a number of customers. What types of batteries can I use as temporary backup when we're actually performing a discharge test? So what is the recommendation to bring in, like a 120 volt battery system? Do you bring in 12 or 10, 12 volt batteries, deep cycle marine batteries, or what is the recommended practice there, Chris?
Yeah, the key is, yes, you can use 12 volt batteries. You may need to bring in some parallel strings though. So for example, on a 125 volt system, your typical design time is anywhere between 3 and 5 hours. But you do have some in the load profile, typically on those systems, you have some high rates. So there's a couple of things. I can't just put in, let's say, for example, that I have a generating station and my batteries are 1,000 amp hour, and I come in with 4 12 volt batteries that are 100 amp hour. I'm probably going to die within the first minute. Not that if you look at the rated capacity on those batteries, oh yeah, they give me 30 minutes. That's enough. There's this phenomenon of lead acid batteries called coup de fouet. And when they, at the beginning of the discharge, the voltage drops precipitously, especially when you try to take energy out in a very fast manner. And so you run the risk of running below the cutoff voltage of your operating equipment. So we recommend at my company, we recommend that if it's VRLA batteries in a telecom application, that we put a minimum of 2 hours of backup in while we're doing that. And on vented batteries, we put a minimum of 3 hours in because they have thicker plates, so the coup de fouet effect's even greater. Coup de fouet is the biggest problem in telecom applications, not utility applications, but even in a utility application, the coup de fouet can bite you in the rear end.
I was waiting for the "it depends" to come out on this one, because we have so many different amp hour capacity battery systems that are out there, and we want to be able to supply DC power in the event of loss of AC, because that's really what the battery backup is doing, right? So we're taking the in-service battery out of service in order to run the load test. Did you have anything to add, John, associated with your experiences?
Yes, practicality comes into play. It's very difficult to bring in 60 cells of flooded products as a temporary battery. So I would say 10 out of 10 that I've seen, there are VRLA batteries either on pallets or bring in a mobile trailer which has batteries already there, and you just plug it in and then so on. So the VRLA batteries are predominantly used as a temporary product. And one thing that you do want to keep in mind is that batteries, and let's say you have them on a pallet or a temporary mobile trailer, make sure they are on charge when they're not being used, because lead acid batteries do self-discharge. And if you leave it parked out in the middle of Texas somewhere and it's 120 degrees inside that mobile trailer, then your batteries are no good when you bring it out there after
Absolutely.
just a few months.
Do
make
your
sure
maintenance
they're on
your
charge.
station battery.
Yeah,
and your
some batteries can take storage a lot longer than others, but I would say at a minimum, make sure they're recharged or refreshed every few months.
Okay. Good responses. Here's one from Khaled Jabbar. I'm interested to learn about battery service test and capacity test as described in IEEE 484-2002. I hope to share that you will share some practical aspects about the test, and who knows about this particular standard IEEE 484. Volney.
I can add something. Well, one first clarification, 484 is the recommended document, that document with the recommended practice for design, installation, and installation of vented lead acid batteries. So probably the proper document to talk about battery testing, like a service test and performance test, is 450 for vented lead acid batteries and 1188 for valve regulated batteries. Now, we have done numerous webinars on that talk about these procedures, kind of explaining what the standard or the document has. So we invite the audience to check the webinars that we have, and well, we will keep doing this. And if there's any specific information, we can be contacted with via email.
Curtis?
Yeah, he asked for, best practices, things that we've learned over time from running these tests. We talked already about a few of them, like having bypass cable if available and so forth. But one thing I want to remind people, there's two different types of tests. Most people are familiar with what's called the time-adjusted method, where, for example, you run a discharge test at the 3-hour rate of a battery, or the 4-hour or 5 or 8-hour rate of a battery, down to the 1.75 volts. And that is a valid test and is very good, especially if you run it at a rate more than three plus hours. If you try to run it at lower rates, like for a UPS, the time-adjusted method will not give you an accurate measure of your capacity. It will give you an accurate measure of the time you have left, but not an accurate measure of the battery capacity and when you're at the knee of the curve. For that, you have to use what's called the rate-adjusted method, which is a little bit tougher to do. You have to run a few more formulas and a few more lookups in the manufacturer tables to run that. But for UPSs, especially, you have to do a different method to get an accurate measure of capacity. Also, on a UPS, if you're hooking a load bank up to the AC output, you need to look up what your inverter efficiency is and factor that into the calculations, because you're losing power through the inverter. The batteries actually have more energy than you think they do, because if you don't take that efficiency loss, you're typically somewhere in the range, depending on the age of the inverter, somewhere in the range of the 93 to 96% when you're fully loaded, or at least 80% loaded on a rate-adjusted method.
The last question associated with load testing is, we touched on it briefly. What is the difference between performance test, modified performance test, service test, acceptance test is defined by IEEE 450. So this is from Khaled Jabbar. And I know that we've covered this in a number of webinars, but just briefly, maybe Sanket, if you could give an overview of each one of those.
Do we have an additional hour or no?
Yeah. So, or we can refer back to the webinar because we did a very detailed associated with each one of those. And it looks like we're 50 minutes into our session. So maybe we'll send a link to one of the webinars. Maybe we'll do that. Yes. Okay.
Right. That cloud cell, I would say, referred to IEEE documents.
Right. So that would probably take 20 minutes in its own right.
Yep.
Omatic question. So Omatic testing is the ability to test a battery while it's in service. And the next, I guess, 5 questions are associated with Omatic testing. The first one is really defined on the Byte2P results. That is a Megger product to measure impedance. And how do we merge 2 different jobs into one document on PowerDB? So a single file for trending analysis. So Volney, do you want to take that one on?
Well, ideally, when you are using the instrument with the software that comes associated with the instrument, which is PowerDB, ideally you should download the results into the same file. In each specific file for each battery will act as a little database, so you can do the trending there. If by any mistake you didn't do that and you created 2 separate files, they can be joined. We can help the customer with that. But in reality, the best thing is to do the download to the same file or use PowerDB Pro or PowerDB Advanced that allow you to do the trending, especially PowerDB Pro. That is kind of something that we can help you individually when you need that. Just send us an email and we can show you how to do things there.
Right. And that was from Mauro Rocca. I apologize. I stopped giving the names out.
I would like to add something to that.
Okay, Sanket.
So yeah, I've come across quite a few people who are not aware that that combining results can be done, or storing multiple results in a file can be done on PowerDB Lite. So people tend to create separate files for separate tests, and that's not the right thing to do because this testing is all about trending and seeing how the values change over time. So just know that even the free software, the PowerDB Lite software, has the ability to allows you to store multiple results so that you can trend the results. And if you have already created separate files, and unfortunately it's not possible to combine those, but if you have those on the instrument, yes, you can download them onto the same file. If you have separate files, you can contact us, Megger Technical Support, and we'll basically get in touch with the factory and they'll help us to combine the results for you, but just keep that in mind.
Or even better, to buy a licensed version of PowerDB and you can do it on site. So that's the sales part of me. The next question is going to be to Andy Sagel. Can we predict a life of NiCad batteries dependent upon the impedance results, and how reliable are doing Omatic tests on NiCad batteries? And this is from Khan Mohammed.
Well, in short, you're not going to be able to really predict a life based on impedance results with NiCad batteries because they have a different discharge profile. So as they discharge, you'll notice like with a lead acid, when it discharges, its voltage drops slowly as its impedance increases. With the NiCad battery, they're going to stay pretty solid until near end of capacity. Then you're going to see that voltage drop off quickly and that impedance will shoot up. So if you go through a NiCad string and you see one with a very high impedance, okay, that's a sign you might have an issue there. But if you're getting good values, it doesn't mean, you don't know where they are in their life cycle. So you really do have to do discharge testing on a NiCad battery as part of the service routine. Now, with that said, like I said, before you run a discharge test, if you're going to be doing verifying your intercell connections, you can use an impedance tester to go through that does intercell connections along with the batteries, because if you do see a real high one, that's an issue. And the only other caveat I would say is that if you have the only thing that would make impedance really rise slowly on a NiCad would be carbonation occurring in that NiCad battery. And that is something that typically takes a very long time to happen. But if you're in a really hot environment, or if you're in an area that has high CO2 levels, then that may increase a little bit.
Curtis?
Yeah, great comments from Andy there. Just a couple of additions. There is one foamed plate battery on the market that's NiCad that allows you to predict life or end of life by the use of a clamp-on ammeter for float current, but it's only for that particular technology, and that's not applicable to all NiCad batteries. Other than that, all of them are going to require a discharge test instead of ohmic testing to determine. The good news is they last a long time. Typical for them to last 20, 25 years plus. And there are batteries out there that are 40, 50 years old that are still providing useful service before they carbonate, as Andy was talking about. So the only drawback there, of course, is you're going to pay a price to get a long-lived battery. And the other advantage to NiCad, of course, is that they're abuse tolerant. You can over discharge them, you can overcharge them, you can put them in cold temperatures, you can put them in hot temperatures, and you just do not see the same deleterious life effects that you see with a lead acid battery, but you pay the price for it in the upfront cost.
The next question is from Ahmed Gayab, and it is, I guess, to Andy, because this is, can I assume the maximum capacity of a byte 3 is the maximum capacity of a cell under test, not a complete string? And I think that's based upon the output current of the byte 3 versus what the byte 2 has.
I think what is being asked there, I think they're asking the voltage that it measures is based upon the individual cell, and yes, that's true. So the voltage limit on it, the 15-volt limit, is for an individual cell, obviously. And the current that it outputs, it's going to inject the current through each individual cell, the test current of 500 mils through each individual cell, where the byte 2 injects 10 amps through the entire string. So each one has its own advantages and disadvantages depending on the type of string and batteries you have.
And I noticed that he asked a separate question on byte 3 on how he adds multiple straps into the report form. And I thought that that was pretty self-explanatory with that particular product, that it would define the number of straps when you're in the middle of a test.
Actually, with the byte 3 actually will auto detect whether you're on a cell or a strap. So you don't need to pre-program it. All you do is just, you go on a battery, it recognizes the battery, and it will say that's cell 1. You go to a strap, it'll say, okay, that's strap 1A. If you now go to another strap, it's going to say, okay, that's strap 1B, 1C, and it'll keep going on like that until you get to the next cell and say that's cell 2. So the byte 3 doesn't require any programming of that nature. It will do that all automatically, and all of that will download automatically into PowerDB.
Right. And we have about 10 more questions. These are in miscellaneous areas. So did you have something to add real quick, Curtis? Because we're running out of time.
Yeah, so I just wanted to, Andy talked about the voltage capability of the different ohmic meters that Megger sells. And so I want to point out, you know, for the competitors that some of you on the call use, the same thing applies about the voltage. If you have a 16-volt battery, you need to make sure your instrument can read that. But the other part that I thought I heard in the question had to do with the amp hour rating of the battery. So for example, you may go to one manufacturer's instrument that says, hey, this is good from anywhere from 20 amp hours to 8,000 amp hours. And the reality is that marketing is going to push the envelope there. Let's put it that way, for certain manufacturers. And because they want to be a me too, they say that they can do these big batteries. I will caveat that when you're dealing with a large VLA cell, anything over 1,000 amp hours, for example, you need to be careful which instrument you use. It needs to use a big enough current signal to accurately measure that incredibly low resistance. And not all manufacturers do that, even though they say they do.
Yes. And that's a very good point, because that's a matter of resolution. So
Yes.
if you get these little handhelds and you put them on a big battery, it looks fantastic because they all read the same. And everyone goes, wow, that's great. But they're not measuring anything. So even the bad ones will read good. You put something on there that has enough current to get the resolution, now you see the difference.
Yep.
The next question is associated with miscellaneous. So these are on the batteries themselves and either associated with a procedure or the actual cells. And the first question is actually for John Kim, because it's related to an Intersys battery, a type GC41. It says, why are flame arresters used on this type of battery? And what are the adverse effects that if they are damaged? Well, there's adverse effects anytime you've got a flame arrestor that's damaged. And I've seen damaged flame arresters or cracks in the top of jars. So probably cover that first and then this specific cell, okay?
Okay, yeah, the flame arrestor number one is needed on flooded products, because when they are on charge, all lead acid batteries will generate oxygen and hydrogen gas, and it will vent. So what you want to do is you want to keep any type of flames or sparks from entering the cell, because inside the cell you have high concentration of oxygen and hydrogen. Why is oxygen and hydrogen bad? Because hydrogen gas, when it gets up to 4% concentration, will have an event, let's call it that. We don't like the term explosion in the battery industry. So it has an instantaneous disassembly event, and you want to avoid that. So you have flame arresters on flooded products, all flooded products, to prevent sparks from entering the cell and also evenly disperse oxygen and hydrogen gas. Now, with if you do not have a properly operating flame arresting vent, let's say the vent itself is clogged up with debris or dust or any kind of things, and it's not operating, then you have a problem. You could have a buildup of pressure if the vent itself is all clogged up, or if the vent is loose and it's just spinning around, then you can have gases come out freely. So you wanna have flame arresting vents on, properly operating flame arresting vents, and you wanna have them on, especially when they're on charge. Now, if they're in storage or if they're being transported from one site to another site, then you do not need the flame arresting vent, because it doesn't have, it's not gassing at that moment. But once you have the batteries on charge, whether it's on float, equalize, boost charge, yes, you need to have flame arresting vents on. And because of our GC41, was it? That's a product that's a large flooded product for utility application. It's about 3,300, 3,400 amp hours. You need to have that flame arresting vent on because of potential for oxygen and hydrogen gas.
He had a follow-up question. What is the normal lifespan of flame arresters, and do they need time-based replacement?
Flame arresting vents are designed to last a lifetime or design life of the products. So if it's a 20-year product, it will last 20 years. Now, every once in a while, you will have these flame arresting vents. Certain types will have these basically a little cap that goes on top to cover the watering hole or in those inside those vents. Every once in a while, they will crack, and you can replace them. You can go to the manufacturer and get a replacement part for that.
We're right at 1 hour, and for all the attendees that are listening in, we are going through all these questions that you submitted. We do have a few more. I want to extend this session another 15 minutes in order to try and hit the important questions that came in recently. So one of them is regarding personal protection equipment when testing batteries. I think this is applicable to everybody that might be out there doing any type of test or construction. The question comes from a number of people, and it is concerning arc flash versus chemical PPE while conducting various tests on station batteries, because we've got PPE associated with the electrical hazards as well as the chemical hazards. So if you're within 18 inches of station batteries, you're required to wear arc flash PPE rating 2. If you're taking specific gravity readings on cells, you're required to wear proper chemical PPEs. Dressed in proper Cat 2 arc flash PPE while doing this test is very cumbersome. Besides arc flash shield, how does one know if your clothing is truly chemical resistant, and how do you balance this when you're performing a test? And Curtis, you do a lot of testing on the field. I'll let you take this one on.
Yeah, so this is an excellent question. I would caveat this with that it seems like the questioner is saying that on all their station batteries, they have to be an arc flash Cat 2. I would suggest that that's their company policy. That is not an absolute rule for everybody. What happens is companies tend to err on the side of what they think is safe. And so they just make these overall mandates and say everything needs to be arc flash Cat 2, hazard risk category 2, without even looking at what the arc flash energy that's available. The problem is it doesn't really make the user safer, as the questioner points out. The thicker the clothing you put on and the thicker the gloves you put on, the more you sweat and the less dexterous you are. So my suggestion would be to actually run an arc flash calculation, which is fairly easy for DC. It's not for AC, but it's fairly easy for DC. The short circuit values of the batteries are published by the manufacturers. And it's fairly easy from Annex D.5 of NFPA 70E. And if you ever need help, send me an email or give me a call. My email will be at the end of the thing. And I can tell you, for a particular battery, here's the arc flash energy at 18 inches at this voltage. And so having to put on that heavy duty stuff is usually overkill. The other part that I would say that people are not commonly aware of, leather gloves, heavy duty leather gloves have an arc flash rating of about 10 to 12 calories per square centimeter, which is in the hazard risk category 2 range. Rubber insulating gloves, like electrical shock gloves, those have a arc flash rating of about 17 calories per square centimeter, regardless of their thickness. The other nice thing about the rubber insulating gloves is obviously rubber is, unlike leather, rubber is impervious to acid or potassium hydroxide solution. So electrical insulating gloves serve 3 purposes. They electrically insulate you from shock hazard. They provide up to 17 calories per square centimeter of arc flash, and they are chemically resistant. That said, they're expensive. And you have to test them every 6 months per OSHA in the United States. The other thing that people do is they err on the side of too big of insulating gloves. So the insulating gloves, you can buy them in class 00, class 0, class 1, class 2, class 3, and class 4. I was at one of our sites the other day and they pulled out their electrical insulating gloves and they were class 2, which is 17,000 volts. We never work on anything over 600 volts. Why do I need a 17,000 volt glove? I need a class 00 glove for most of the stuff that you deal with. A class 00 glove will work for 500 volts AC, RMS, or 750 volts DC. So most of your applications that's plenty thick enough of a rubber glove. The other part that I would talk about is oftentimes for handling electrolyte, when I'm dealing at the lower voltages where I don't need arc flash protection, I really like the gloves that are cut resistant, and they even make them in arc flash gloves. You can buy arc flash gloves that have the rubberized palm, and that obviously the back side of that is susceptible to acid with the Nomex fibers that are on it, or the wool fibers, or whatever you have. But the front side, which is where you typically get your acid on your palm and the fingertips, those are protected with a latex, or I forget what the other chemical is. It's typically a coating for a cut resistance glove that is also acid resistant.
The next question comes from Joseph Daniel, and he is interested if there's a way to replace a cell or battery while the string is in full service. Curtis again.
This is a subject I wrote a paper. The reason I'm answering this one, I wrote a paper on this exact subject for BATCon, which is a battery conference back in 2013, and there are three ways to do it. The safest way to do it is what we talked about before, about bringing in a temporary string. So I can bring a temporary string in, and then I can disconnect, or strings, depending on the capacity that I need. And then I can disconnect the string that I need to replace the cell in and work on it, quote unquote, relatively more safely. If I have to do it while it's online and I can't bring a temporary string in, the electric utility industry developed a practice where they use a diode out of an SCR rectifier that's rated at several hundred amps, and they put that in an insulated box, and then they use the diode to do that. And it's a multi-step process. It's a 13-step process to do that. I developed a procedure where you can use a car battery. You don't have nearly as much backup time to get that bypass done, but it's possible. Both of those are very scary procedures if you've never done them before. And so it's possible to do, but the first time you do it, you're going to be scared. And it's not that it's dangerous to your health, it's dangerous to the load. And so it can be done. It's just not a simple procedure. It's always best if you can do it with a parallel string online, and then you can take this one offline to work on it.
Anyone now? All right. This is kind of a generalized question, why solvation occurs in batteries, from Omar Gupta. And this goes back into the actual chemical activity within a battery and charging. Andy, we haven't heard from you in a while.
Sure. Sulfation is a natural, I guess, a consequence of a battery as it discharges. A lead acid battery as it discharges, the lead in it will turn into a lead sulfate on the plates. And as you recharge the battery, the process actually does reverse itself. And the problems you can really run into is when you're not recharging the battery back up fully. When you're not recharging it fully, then the negative plate can remain partially sulfated. And the problem with that is the longer it remains that way, the harder it is to reverse it. And this is one of the reasons you run an equalization or a boost charge, is you're trying to break down the sulfation crystals that have appeared on, that have developed onto those plates. And that's the actual function of that actual equalization. But again, sulfation is just a natural process that you're going to get from the discharge of the battery.
John?
Yeah, and adding to what Andy said, the sulfation mainly happens for three reasons. One, if you discharge the battery and you do not recharge fully or leave the batteries in a discharge state. Two, you have your batteries on float, but you're floating the batteries too low. You're undercharging the batteries, then you will start to sulfate. Third is when you have your batteries stored on open circuit too long, and depending on the type of battery that you have, whether it's flooded or valve regulated or lead calcium or lead antimony, you have different duration, and you have to know what you have and follow that manufacturer's guideline. So those three items are the main causes of sulfation, and as Andy mentioned, that as they become harder and harder, those crystals grow and it becomes hard, then you will have your capacity suffer and your life suffer as a consequence of it.
I think we have time for 2 more questions, and I've been watching the attendees associated with this particular event, and they've all stayed on since the beginning of the hour. So the 2 last questions. One is regarding the disconnects for DC distribution systems as related to batteries, and concerning battery banks in a telco, telecommunications environment. Are there an actual requirement to have disconnects on your DC system? Curtis?
So good question. In telco, the FCC has some best practices. They're just that, best practices. However, if you have an outage, they will beat you up over the best practices if you're not following them. And under their best practices for central offices in telco, you should not use battery disconnects because they're a single point of failure for central offices only. That said, I'm a big fan of disconnects in other applications, especially for VRLA, especially for short strings. And the reason I'm a fan of them is it makes maintenance a little bit easier. From a replacement perspective, from taking an ohmic reading perspective. So when you take ohmic readings and let's say, for example, you're doing 24 volt strings and you've got 2 parallel strings, and I try to take an ohmic reading on 2 parallel strings online, I'm reading 2 parallel resistances, and I can have an error as much as 33% in my reading. So it's always good to take an ohmic reading with a parallel string disconnected. If you're only dealing with a single string, you don't have to worry about that. But for parallel strings, I'm a big fan of disconnects, and even for non-parallel strings, I'm a big fan. Other than the caveat that I pointed out that the FCC is not a fan in central offices.
I know that Walney's had an experience with parallel strings associated with the cruise industry, and using a byte 3 and the CT to go and measure the current that's flowing through that particular battery string. And he devised an actual procedure for that, and Andy Segal as well. So just to shorten the response for the time, I know that we also at Megger take that into consideration. That question came from Kevin Tuttle, sorry. And the next question is from Mark Lambert. And it is how to separate battery charger to feedback a DC panel while removing the existing battery for replacement. How do you use a separate battery charger to backfeed a DC panel when you're removing an existing battery for replacement? Curtis?
So it's key that you buy a battery charger that is rated, or a rectifier, depending on the industry that you're in, that is rated for operation of the load without batteries. And what that really means is they've spent some extra money on capacitive filtering on the output. Your battery acts as a natural capacitive filter. No DC that's created from AC is a perfect flat line. There's always some ripple on there. And so some of the loads don't like the ripple. And so you need some filtering, and the batteries provide that natural filtering. So there's a term that they use in the industry, and it's escaping my head right now. Maybe one of you guys can pop in as to what they call those types of chargers that you can use without a battery connected to them. Andy's trying to think of it too. Anyways, it has extra capacitive filtering. So what you're looking for is something under 100 millivolts peak RMS AC is really what you're looking for on the charger without a battery connected.
Actually, I want to do one more question for the group. This one's interesting. It comes from Chile. Benitico Beltran asked, how is the behavior of different types of batteries with geographical height and low temperature? So this is basically a battery selection type question, and some of the criteria that might go in based upon the elevations being very high and the temperatures being very. John, you want to try and take that one on first?
Sure. Temperature definitely will affect batteries, especially if you have lead acid batteries. Higher temperature, you get better chemical activity, and you get slightly higher capacity out of the batteries. But at the same time, you have higher corrosion, so you get less life. Lower temperature slows down the chemical reaction, and you get less capacity out of batteries. Now, depending on the type of batteries that you have, that definition of low temperature will vary. Yeah, temperature definitely has an effect. As far as altitude goes, the batteries that we have tested, they will operate in altitudes that people can live in. So I don't think you have to worry about the altitude. Humidity does also affect slightly, but not to the degree that it will greatly affect the capacity and life of the products. So temperature is, I would say, number one factor.
And Andy?
Yeah, the one thing or two things I'd just like to add into that is, one, if you're dealing with lithium ion, as you get into the colder temperatures with that, your rate of charge with it will slow down because the maximum rate of intercalation gets slower as you get to those lower temperatures. Because your lower temperatures, what happens? Your molecules move slower. Okay, so they can't, the reaction time slows down. The only other thing I'd like to say about the altitude is where that would have an impact really is more on your arc flash calculations. So that for a safety factor, you might have to take that into account depending on the altitude.
And Curtis, to wrap it up.
The only other thing that I would add on once again, I agree with the comments on the altitude. It's very little effect on your battery choice. Your correction factors for temperature you can find for lead acid in IEEE 485. That will give you generic ones. Obviously, the manufacturer can give you exact ones for the battery model, but the generic ones are going to be pretty accurate. So just to pick an example, for example, if you're at a high altitude where you're gonna see temperatures down to, for example, 0 degrees C, which is 32 degrees Fahrenheit, you would expect your capacity of your lead acid battery, and I don't have the KT factors right in front of me, but down at 0 degrees C, I'd expect maybe 50% capacity. Going to be quite a drop off as far as the capacity. Now I'll get better life out of the battery, as John said, but it's going to be quite a drop off. If I'm going to deal with really low temperature environments, my battery of choice is a NiCad every single time. If I want the capacity and the lifetime, it's just a better battery for cold temperatures.
And Volney?
Comment about the previous question. I think I don't have anything to add on this one, but on the previous question, the term that you were looking for, Curtis, was the battery eliminator. I think.
Thank you.
And no, thanks to Tom Carpenter who gave us the tip there on the in the question session, the question panel.
Thanks, Tom.
As well as Zach Milkey also caught that.
Yeah.
Okay, good.
Right.
Thanks.
Well, I'd like to thank our panelists today, Andy Segal from Valley Forge, Pennsylvania, out of the Megger manufacturing site there, John Kim with Intersys Batteries, Volney Naranjo, a senior applications engineer out of Dallas, Texas with Megger, Sanket Bolar, applications engineer out of Dallas, and Curtis Ashton with American Power Systems. this concludes our session panel today, and I thank all the attendees that were listening in. The next slide, I believe, has a survey and contact information associated with our emails. And after you log out of this particular session, you will be getting a webinar survey. This is our first You Asked, We Answer survey. So please put in your comments on what you thought went right, what you thought we could do better. And we look forward to the next webinar session. So you can check that out at us.megger.com and select the webinar area associated with our banner. Thank you.
Thank you.
That's all.
Bye. Thanks.
Thanks, guys.
Thank you. Have a good week.